Hello, this is Deep Thoughts with Deegan, and today I'm going to be talking about recursive composition. So I have a little bit right here, well, let's get started. So this right here is a recursive composition of some function f of x. G of x is whatever the nth composition of the function f of x. It's pretty simple right there. Now, we don't know how many compositions we're doing. I mean, right here it looks like we're doing at least 1, 2, 3, at least 4, potentially 5, because we have these ellipses here that says there's something going on there. But this is just a general form. I usually only write it with like 3 terms. We do f of f of x. But I just want to show you how redundant this is. If you're doing like 5 or 6 of these, this is terrible. You don't want this. So I have a notation I use for this. Call it psi notation because it's just capital Greek letter psi. And inside I have parentheses where we got f of x in this case, right? And for this, I have a subscript right here. That's whatever number I want. So when I don't know what number composition I'm looking for, I just put a capital N, right? That's going to be the same as this function, g of x, right? So the way this works is you just take n compositions, and sometimes it'll diverge into a multivariate function in terms of both x and n. So it's predictable. Depending on how many of these you have, it'll turn into a constant. So you can figure out the formula of your nth composition of your function. And that's not just like putting all of it together. Sometimes you can like condense it. So that's what we're going to look at next. So I'm looking for 2 of them right here. These have pretty similar answers, where I'm looking for the nth composition of a constant c and the nth composition of just x. And if you look at this one right here, there's nothing to plug anything into. So what that ends up looking like is, let's say we just plug in it to itself. Well, we get c. What I like to do is I like to just write down a couple of these. Usually I'll do 4. For this one, I'll do 3. I just start with their bases, and then I plug them into themselves. So if I plug in c to c, nothing to plug it into. So it stays at c forever, right? So it's always going to be equal to c right there. Here, plug in x to x, x. Plug in x to x, x. No matter how many times you go, always going to be x. These 2 are, as far as I can think, the only ones that'll actually do this, where they're self-referential no matter how many times you plug them into themselves. But I'm going to show you some ones that don't do that, but you can still predict. I have the nth composition of x plus 1 for the first example that has predictable outcomes, not just itself. Now I'm going to say right here that the nth composition of x plus 1 is equal to x plus 1 plus n. For each composition, right? So there's 2 ways to prove this. The first one, which I'm going to show first, is you just start with 0. The 0th composition, right? Just x plus 1, okay? First composition, plug in x plus 1 there. Plus x plus 1 plus 1, that's x plus 2, right? Let's check it right here. X plus 1 plus 0 is 1. X plus 1 plus 1, x plus 2. All right, let's try it again. 2 for our second composition. It's going to be x plus 1, plug it in there, plus 1, because we have that right there, plus 1, x plus 3. And actually, no matter how many times we do it, it's always going to end up like that. Now, there is another way to prove it, that if you know what you're doing, it's a lot easier. If you don't know where to start, this is the best way to go. This is usually how I start with most of them. But once you kind of have a pattern down, it's a lot easier if you actually do algebraic manipulation for it. And I'll show you how to do that. So another way to look at this is just a bit more methodically, is I'm just going to take, let's find the first composition first. So I'm looking at the first composition is going to be equal to, I plug in x plus 1 plus 1, right? X plus 2. Okay. So from there, I already know this is true, right? And obviously I know the 0th composition is just the function itself. So I can tell that there's the difference of 1, right? So that's already a little bit of a clue that what we're looking for here is something we're adding or subtracting. What you can do from there is let's look at what happens if we plug in. So let's say we want psi of n, right? Or let's say we want psi of 2. Now, because we know psi of 1 and we know what's going in there, we can say that's going to be psi of 1 plus 1. Yeah, psi of 1 plus 1. Okay, so, well, because this can go in there, we know psi of 1 is x plus 2, right? It has to be x plus 3. Keep doing this, you're going to have the same thing happen, where you have your x plus 1 every time, and it's going to add n times. So that's how we can get, that's another way we can get that I actually like more because it takes so much less space. Also, it feels a little bit easier. So here's another one I'm going to look at, and I'm going to use another different method to look at this one. So what I'm going to do for this is I'm going to take whatever this function is, x to the a, right? Now I'm going to go again, x to the a, and again, x to the a, to the a, to the a. Now, when you're looking at this, you can use exponent rules, right? So this right here is actually going to be equal x to the a squared, right? This right here, because when you put a power to a power in parentheses, to an exponential in parentheses, you can put it back in. You can multiply it in. So right here, we have the same thing here. A times A times A. It's going to be x to the a cubed, right? So now remember, this is n equals 0. That's like the worst 0 I've ever done. That's n equals 0, n equals 1, n equals 2. Okay? So what this is going to become, this one's kind of easier to look at. It's going to become x is always there, to the a, and notice how it's going to a power of n plus 1, right? If we look at this, these are pretty self-explanatory. We got 1 plus 1 is 2, 1 plus 2 is 3, so on. Now right here, 0 plus 1 is 1. A constant to the 1 is itself. So there, it actually works there also. So now what I'm going to do after this is I'm going to show you one that is a little bit different, that is a lot more difficult to figure out, but you can use some patterns to help find it. For my last example, I'm going to show you this one. I actually have not been able to figure out the nth composition of the natural log of x, but somehow I ended up finding the derivative of it. So what I'm going to do here is I'm just going to start with my first function, ln of x, right? The derivative of that, the derivative of the natural log of x is equal to 1 over x. So we have our first case. Now, a little bit more difficult. I'm going to look for the derivative of our first composition, which is the natural log of x, right? To do this, we're going to use chain rule. First function is natural log of x, derivative of that, 1 over x. Same thing down here, natural log of x, 1 over x. Now we're going to put this together, right? So we're going to end up with 1 over natural log of x, ln of x, times x. First derivative of the derivative of the first composition is 1 over x ln x. So now for these next ones, I'm actually going to do them separately because they take a little bit longer. So I went ahead and did the next two. You see, they get very big, but I simplified them down a little bit. For this first one, we got 1 over x. Right here, we got 1 over x ln of x, right? And if you remember, the 0th composition of the function is the function itself, right? So it's 1 over x psi 0. Right here, this is when it starts getting a little bad. It's 1 over x ln of x times ln of x. That's x psi 1, psi 0. Down here, it's going to go all the way. We get x. This is psi 2, ln of x. Right here, this is ln of x, which is psi 1. This is ln of x, which is psi 0, right? So if we look right here, we get all of these together, right? Every single time it just adds in or multiplies in another psi. So we can actually use this right here, where we have 1 over x. We can use pi notation, where we have big pi from, I'm going to use j actually, from j equals 0, right, to whatever composition we're looking for, because this actually does not work at 0 because we already have the thing itself. So what it's actually going to look like is 1 over psi j, right? Looks kind of scary. But the explanation right here is every single time we're multiplying in another psi 0, psi 1, psi 2. And if you use chain rule right here, because we usually have ln of x, 1 over x, right? Then we end up with psi of n minus 1, right? And the derivative of that is going to be the same thing, where we go 1 over all the way down with these, right? So we're actually, every time, we're just multiplying in this, or we're just multiplying in psi of n minus 1, right? So just by chain rule, you can figure this out that way. All right, that's the end of this video. Thanks for watching. I'll see you next time. So it's Deep Thoughts with Deegan.